This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 3 of Quantum Wonders. In today's episode, titled Quantum Tunneling, Magic or Physics, we're going to unravel the fascinating principles behind this mind-bending phenomenon that seems to defy the rules of reality. So, grab your curiosity and let's dive in. An electron in your smartphone sometimes appears on the far side of a barrier it doesn't have the energy to climb. No cheat codes, no hidden batteries, just physics. In today's story, we'll follow that rule-breaking hop and ask, where exactly does the impossible begin? That impossible hop isn't rare quantum trivia. It's a workhorse quietly running both the cosmos and your gadgets. Inside the sun, countless protons rely on this same trick to fuse and release the light that reaches Earth. In your devices, engineered structures just a few atoms thick use it to store and erase the bits behind your photos and messages. Engineers don't treat this as mystery. They treat it as a design parameter, like an extremely temperamental teammate who follows strict rules but only probabilistically. Shift the thickness of a layer by a fraction of a nanometer, and suddenly currents drop by orders of magnitude. In labs, microscopes read tiny changes in this current to map surfaces almost atom by atom. So instead of asking, is tunneling real? The practical question becomes, how precisely can we shape it, and what breaks if we get it wrong? On paper, tunneling looks like a niche oddity in an equation. In reality, it's a gatekeeper that decides which ideas ever leave the whiteboard. Material scientists weigh whether a new insulator will quietly leak charge over years, sabotaging data long after a product ships. Nuclear physicists revisit old models when tiny tunneling tweaks rewrite estimates of a star's lifetime. Even in quantum computing, qubits must sit in an uneasy truce. Tunnel too easily and information spills. Too reluctantly and useful operations crawl. Tunneling isn't just allowed, it's budgeted, negotiated, and sometimes feared. In classical physics, a barrier is a simple yes-no decision. Either you have enough energy to cross or you bounce back. Quantum mechanics replaces that crisp boundary with a probability slider. To see how far that slider can be pushed, physicists solve the Schrödinger equation for different barrier shapes and heights, then check their math against exquisitely sensitive experiments. One striking outcome: details matter brutally. A rectangular barrier, a triangular one under a strong electric field, or a double-humped barrier all give different leakage profiles. Stack two barriers with a thin region between them and something surprising happens. At very specific energies, tunneling is dramatically enhanced. Electrons effectively resonate between the two walls, boosting their odds of appearing on the far side. Devices called resonant tunneling diodes exploit this to deliver a current that rises and then falls as you increase voltage, a behavior that would look impossible in a purely classical circuit. Physicists also flip the usual question. Instead of, what's the chance of getting through this wall, they ask, how long does the particle spend inside it? That's where the folklore about faster-than-light tunneling started. Some measurements of the tunneling time seem to suggest that increasing the barrier thickness doesn't increase the crossing time in a simple, linear way. But when researchers carefully track what information can actually be transmitted, relativity stays intact. No signal beats light across the gap. Beyond electronics, tunneling quietly governs chemistry. When molecules rearrange their bonds, atoms sometimes tunnel between nearby positions instead of climbing the full energy hill. At room temperature, this can tweak reaction rates. At cryogenic temperatures, where classical motion nearly freezes, tunneling can dominate. Enzymes in living cells are suspected of harnessing this, effectively pre-aligning reactants so that certain nuclear motions can tunnel and speed up vital processes like hydrogen transfer. Your challenge this week: pick one everyday object, an LED, a GPS receiver, a digital camera, and trace how many layers of its operation ultimately rely on quantum rules where no is really maybe with a tiny probability. Each time you hit a barrier that isn't absolute, Note what would fail if nature were strictly classical. By the end, you'll have a personal map of where the world you use crosses into the quantum one. In sports terms, tunneling shows up as a kind of ultra-selective transfer window that only opens under very specific conditions. In certain nuclear decays, for instance, alpha particles leave heavy atoms by slipping through a potential barrier instead of vaulting over it. Tiny shifts in nuclear structure can change lifetimes from microseconds to billions of years. In superconductors, paired electrons can tunnel in lockstep across thin gaps, creating Josephson junctions that underpin ultra-precise voltage standards and some qubit designs. Atmospheric scientists care too. In cold interstellar clouds, hydrogen and other light nuclei can tunnel in frigid dust grains, helping stitch together complex molecules long before stars ignite. Even metrology leans on it. Calibrated tunneling devices define reference currents with extraordinary stability. When you zoom out, tunneling isn't an edge case, it's a quiet rule setter, fixing which processes barely happen and which effectively never stop. Soon, tunneling won't just be a curiosity, it will be a design constraint you can't ignore. As circuits shrink, stray tunneling will blur the line between off and on, forcing engineers toward exotic stacks of 2D materials and devices that treat leaking as a feature, not a bug. Quantum processors will choreograph coordinated jumps across tiny gaps, while ultra-sensitive sensors use rare events the way seismologists read faint tremors to infer distant quakes. Today's leaks become tomorrow's dials, so tunneling ends up less like a loophole and more like a quiet design language for reality, setting which paths are merely unlikely instead of forbidden. As labs learn to tune those unlikely paths, expect new tools, cancer-targeting beams that spare healthy tissue, ultra-stable clocks, even sensors that read Earth's tiniest shivers through quantum flickers. Before next week, ask yourself, 1. Where in my life or work do I currently see an impossible barrier? And if I treated it like a quantum tunneling problem, what tiny but persistent low-energy collisions, repeated emails, daily practice, micro-experiments could eventually get me through? 2. If I had to pick one specific energy boost, like learning a key concept from the episode, wave functions, probability amplitudes, or barrier height, more deeply, what exactly would I study or test today to change the odds of tunneling past that barrier? 3. Looking at the examples from the episode, like electrons crossing barriers in semiconductors or nuclear fusion in the sun, where in my current projects am I underestimating the power of many tiny probabilistic attempts? And how could I deliberately increase the number of attempts I make this week? This was OwlUp, your daily step forward. This series continues with more chapters on OwlUp.co. Visit OwlUp.co to access the complete course and continue your learning journey. See you there!